Hello, and welcome to Chapter 6. Chapter 6 is a little bit of a replay of what we've looked at before. It's dealing with continuous variables. Chapter 5 we looked at discrete variables. In Chapter 6 we're looking at continuous variables. This is anything that can have a decimal point. Lots of measurement, height, 1 meter in 5 centimeters, 1 meter, 5 centimeters, 2 millimeters, micrometers, nanometers, so on and so forth. Temperature, it is currently 100 degrees outside, 100.1, 100.2, so on and so forth. Some common continuous distributions are the normal distribution, and we've talked about the normal distribution before. Another common continuous variable is the uniform distribution, and the uniform distribution again is drawn by a curve, but this does not change. You could think about the uniform distribution, and it does not go on forever. The uniform distribution goes on forever, but the continuous normal distribution goes on forever, but the uniform distribution stops. So we say it goes from point A to point B. For instance, this could be like birthdays. If you think about each month being 1 for January, 2 for February, so on and so forth, and you think about the child birthing procedure as being purely random, which we know it's not, just based on some weather-related patterns. But you could think it would be modeled after the uniform distribution. So each month there were the same number of babies born each month. Okay? So this models that situation. Another continuous distribution, as you see on page 218, is the exponential distribution. The exponential distribution goes forever in both directions, and this has been used to model radioactive decay. It's sharp at first, and then it slows down over time. So different types of distributions. The one we will focus on the most in this class is the normal curve. It's the one that's most prevalently used in intro statistics classes and even upper level statistics classes as you advance to grad school. Okay. The normal distribution is symmetric, and again the mean is in the center. This should all be reviewed, and we call the mean mu. We know by the empirical rule that this is broken up into standard deviations, and those standard deviations go on forever. And you should remember the 68, 95, 99.7 rule. And that states that from the mean, one standard deviation away from the mean, and these should be equidistant, is 68% of our data. Now, what does that mean? Well, I've been working with a problem lately, and it's talking about filling medicine bottles with 10 ounces of liquid. If we set the fill process to be at 10 ounces exactly, we would say that the mean was 10. And what we mean is 10.0 repeating. In mathematics, that's shown like this. And so, because it is absolutely impossible to fill a bottle of medicine with 10.00000000000 ounces forever repeating, because it's going to be either slightly higher or slightly lower than 10 just by the sheer nature of measurement. We say that half measurement falls on a normal curve, we say that half will be below 75, or excuse me, half will be below 10, and half will be above 10. Now, this standard deviation, what I'm showing with the green curve there, if you can see, and if you cannot see, I would just erase this area, which lies one standard deviation away from the mean, contains 68% of our data, which means if we are trying to fill at 10.0 ounces, we expect that 68% of the bottles will have be within one standard deviation of 10.0. You might ask me how to find the standard deviation, or how do we know? Generally, it'll be given to you. From now on, we will be given it. It will be given to us, or we will find it in Excel. Okay, we'll be doing that just to make our calculations quick. Because the normal curve varies depending on the situation. We could be filling Coke bottles, we could be filling medicine, we could be measuring the heights of children, we could be measuring the heights of adults, we could be measuring temperatures of far off distant planets, we could be all sorts of things. The normal curve will change depending on the situation. So always the same shape, but this could be 10 ounces, or this could be 200 degrees Fahrenheit. This standard deviation, although it will always be the same distance on the curve, this standard deviation could be 1, and this standard deviation could be 10. They're still normal curves, but they have different parameters. So if this standard deviation is 1, it's very easy to label this. It's just 11, 12, 13, and 9, 8, 7. If this normal curve has a standard deviation of 10, then again, you can fill this in to 10, to 20, to 30, 190, 180, 170. Very easy to label these normal curves. Now, my writing is a little messy, but they should be even, symmetric, perfect. If you're a great artist, it will be fine. I draw mine quick. Now, you know, we've got these stepped off in standard deviation, so I could ask you the question, what percent of bottles were filled between 9 ounces and 11? And your answer would be 68% of the bottles. I could say, what percent were between 8 and 12? And your answer would be 95% of the bottles. The normal curve is very, very prevalent, and because it's so prevalent and used in so many applications, there has to be a way to standardize it. And what we're going to do is look at how to make this a standard normal curve. So, let's go back to filling the medicine. If I fill at 10 ounces and I have a standard deviation equal to 1 ounce, 11, 12, 13, 9, 8, 7. It would be very simple to map this to a standard normal with a mean of 0 and a standard deviation of 1. This will make computations very simple. A mean of 0, standard deviation of 1, 1, 2, 3, negative 1, negative 2, negative 3. And this is just a one-to-one mapping. You can see that here 0 represents 10, so on and so forth. A standard normal, we give the symbol z. Z equals standard normal. So, how do we get real life, mean of 10, standard deviation of 1, how do we get that to a standard normal? We do it with the z-score formula, which is given like this, x minus mu over the standard deviation. So x minus mu, mu is